For centuries, humanity has wrestled with the ultimate question. How did everything begin? Not just life, or planets, or stars, but the entire universe itself. Did it simply exist, timeless and eternal? Or was there a moment, a singular instant, when the fabric of reality itself burst forth from nothing at all? For most of human history, and deep into the modern scientific age, the very idea of a cosmic origin, a universe with a definite beginning, was met not with curiosity, but with profound resistance, even outright hostility. It clashed with deeply ingrained philosophical views, and perhaps a subconscious fear of the unknown that lies before the very first second. In 1917, a towering intellect of the 20th century, Albert Einstein, published his groundbreaking paper on cosmology. His equations of general relativity, a monumental achievement in understanding gravity and space-time, naturally hinted at a dynamic, evolving cosmos. Yet, this brilliant mind, a man who dared to rethink space and time itself, seemed to recoil from the implications of his own work. Faced with solutions that suggested a universe that must either expand or contract, Einstein made a remarkable, almost desperate adjustment. He introduced a new term into his elegant equations, the cosmological constant. This was no simple mathematical oversight. It was a deliberate, philosophical choice, a subtle tweak to force his universe to remain static, unchanging, and eternal. Think of it like adding a hidden counterweight to a finely balanced scale, not because the physics demands it, but because you desperately want the scale to show a specific, preordained result. Einstein later, allegedly, referred to this as his biggest blunder, a regret born from hindsight. But in 1917, it was a fundamental reflection of the dominant scientific worldview, a deep-seated preference for a cosmos that had always been, and would always be, a universe without the unsettling drama of a beginning. Yet truth, as they say, has a way of asserting itself, often through the most unexpected channels. Two figures, working independently and largely unaware of each other, unknowingly began to dismantle Einstein's carefully constructed static universe. First, the brilliant Russian mathematician Alexander Friedmann, in 1922, meticulously re-examined Einstein's equations. His solutions were clear. The universe could, and indeed should, be expanding or contracting. There was no need for Einstein's artificial constant. Friedmann's work was purely mathematical, a testament to the raw power of abstract thought. Then came the Belgian priest and physicist, Georges Lemaitre. A man of both deep faith and rigorous scientific inquiry, Lemaitre took Friedmann's mathematical insights a critical step further. In his 1927 paper, Lemaitre not only independently derived the expansion of the universe from Einstein's own equations, but he courageously proposed a physical origin story. He called it the hypothesis of the primeval atom, or sometimes the cosmic egg. Lemaitre dared to suggest that the entire universe, with all its stars and galaxies, was once compressed into an incredibly dense, hot, primordial entity that then began to expand. The reaction from the scientific establishment was almost universally hostile. Lemaitre's idea, though rooted in the very mathematics of general relativity, felt uncomfortably close to the concept of a moment of creation from religious dogma. It was seen as theological intrusion into the hallowed halls of physics. Even Einstein, the architect of the very theory Lemaitre was extending, was dismissive. Faced with Lemaitre's presentation, Einstein delivered a now infamous rebuke. "Your calculations are correct, but your physics is abominable." This extraordinary encounter reveals a profound truth about the birth of the Big Bang theory. Its first, and perhaps greatest, hurdle was not a lack of observational evidence. Indeed, the mathematical seeds of an expanding universe were already present in Einstein's own work. The true impediment was a deep-seated psychological and philosophical bias within the scientific community itself, a reluctance to accept a universe with a finite history, a cosmos that had not always existed. This intellectual inertia, ironically, blinded some of the greatest minds to the revolutionary truth hidden within their own equations. It was a clash between the comforting desire for an unchanging cosmos and the disruptive, unsettling, yet ultimately more profound idea of a universe with a dynamic past and a very definite beginning. For centuries, the night sky was a canvas of unchanging mystery. Stars, fixed in their celestial dance, nebulae, faint and enigmatic smudges of light. But how could humanity, bound to a single planet, ever hope to peer through the veil of time and truly see the universe in motion, to witness its birth and its grand, ongoing story? The answer, surprisingly, lay not in powerful telescopes alone, but in the subtle language of light itself. Our cosmic detective story begins, perhaps unexpectedly, in the quiet, dusty landscape of Arizona at the Lowell Observatory. It was there, starting around 1912, that a meticulous astronomer named Vesto Slipher embarked on a painstaking quest. He wasn't looking for cosmic expansion. He was simply trying to understand the nature of those fuzzy, spiral-shaped nebulae, which at the time many believed were merely gas clouds within our own Milky Way galaxy. Slipher, armed with a spectrograph, a device that breaks light into its constituent colors much like a prism, began to analyze the light coming from these distant objects. What he observed was revolutionary, though its full implications wouldn't be grasped for years. He saw that the spectral lines from almost all these spiral nebulae were systematically shifted towards the red end of the spectrum. This phenomenon, known as redshift, occurs when a light source is moving away from an observer, stretching its light waves like the sound of a receding siren dropping in pitch. The faster the object moves away, the greater the redshift. Slipher's data unequivocally showed that these nebulae, which we now know are vast galaxies, each containing billions of stars, were not only moving, but they were fleeing from us at truly astonishing speeds, some at hundreds of kilometers per second. He had the undeniable evidence, the cosmic fingerprints, but the grand narrative, the universe-altering context for what he was seeing, was still missing. The stage was set. The theoretical framework of an expanding universe, however initially dismissed, had been laid by minds like Alexander Friedmann and Georges Lemaitre. But scientific progress, much like the universe itself, often requires more than just brilliant equations. It demands observation, empirical proof that can break through established dogma. And that proof would emerge from the colossal 1920s, high above the smoggy sprawl of California, at the Mount Wilson Observatory, home to the most powerful telescope of its era. Here, the legendary Edwin Hubble took center stage. His name is etched into the very fabric of cosmology, and rightfully so. But behind almost every scientific giant stands a team, and in Hubble's case, one figure, too often relegated to the shadows, played an absolutely indispensable role: Milton Humason. Humason's journey to the forefront of astronomical discovery was anything but conventional. He started at Mount Wilson not as a scientist, but as a janitor, then a mule team driver, hauling supplies up the mountain roads. Yet, he possessed an extraordinary innate talent for observation, a keen eye, and an unwavering patience that few professional astronomers could match. He mastered the incredibly difficult art of capturing the faint, ghostly spectra of distant galaxies, gathering the crucial data that Hubble needed to connect the pieces of this cosmic puzzle. By 1929, the collaboration between Hubble and Humason culminated in a groundbreaking publication. Their key insight wasn't merely confirming Slipher's redshifts. The true revelation, what we now call the Hubble-Lemaitre law, was the direct correlation between a galaxy's distance from us and the speed at which it was receding. The further away a galaxy was, the faster it appeared to be moving. This wasn't just a handful of celestial bodies fleeing. This was a systematic, universe-wide phenomenon. This discovery, this cosmic smoking gun, forced a radical rethinking of our place in the cosmos. It wasn't an explosion in space, scattering debris through a pre-existing void, like shrapnel from a bomb. That's a common misconception, one that limits our understanding. Instead, the evidence pointed to something far more profound. It was an expansion of space itself. Consider this: picture dots drawn onto the surface of a deflated balloon. As the balloon inflates, the dots move further apart from each other. Crucially, no single dot is at the center of this expansion, and the further apart any two dots are, the faster their relative separation appears to be. Every dot sees every other dot moving away from it. This analogy helps us visualize the astonishing reality. The very fabric of the universe, space-time itself, is stretching, carrying the galaxies along for the ride. And with this empirical validation, the elegant, yet initially rejected, mathematical predictions of Alexander Friedmann and Georges Lemaitre were dramatically vindicated. Their equations, which had suggested a dynamic, evolving universe, now had the observational proof they desperately needed. Einstein's blunder, his cosmological constant, began its slow, reluctant retreat from the scientific stage. Now consider the profound implication of this expanding universe. If all galaxies are flying apart from each other today, what does that tell us about yesterday? And the day before that? Playing the cosmic movie in reverse, we rewind the tape of time. If today, galaxies are separating at immense speeds, then yesterday, they must have been closer together. Billions of years ago, they would have been far, far closer. And if we continue to rewind, tracing the trajectories of every galaxy back through time, the logical conclusion is inescapable. All the matter and energy in the observable universe must have, at some unimaginably distant point in the past, been compressed into an extraordinarily hot, dense state, a singular point of origin. This observational evidence, this cosmic backward glance, transformed Lemaitre's hypothesis of the primeval atom, once dismissed as abominable physics, into a compelling, testable scientific hypothesis. The universe, it seemed, did have a history and a very definite beginning, a faint hum, a whisper from the dawn of time, permeates the very fabric of our universe. It is not silence, it is the oldest sound, the most ancient light, a direct echo of creation itself. For decades, scientists had theorized about the universe's violent beginning, but to truly prove it, they needed more than just mathematical elegance or the outward rush of galaxies. They needed a direct message, a fossil imprint, a photograph from the earliest moments of existence. This cosmic evidence, a discovery that would reshape our understanding of everything, lay hidden in plain sight, waiting to be found. Yet, the story of this profound revelation is not one of a simple, immediate accident, but a more complex tale, steeped in both brilliant foresight and an almost tragic oversight. The first notes of this primordial symphony were actually heard, theoretically at least, long before anyone truly listened. In 1948, a visionary team of physicists in the United States, George Gamow, Ralph Alpher, and Robert Herman, were meticulously piecing together the physics of the early universe. They made an astonishing prediction. If the universe had indeed begun in an unimaginably hot, dense state, it would have released a colossal flash of light, an overwhelming burst of energy. Over billions of years, as the cosmos expanded and cooled, this light would stretch, losing energy, morphing from blinding gamma rays into a faint, cold glow, still detectable today as microwaves, filling every corner of space. They even had a remarkably accurate estimate for its temperature, around 5 Kelvin, just a few degrees above absolute zero. This was a groundbreaking insight, a theoretical smoking gun for the Big Bang. But in a twist of scientific fate, their profound work was largely ignored, a brilliant prophecy forgotten by a physics community perhaps not yet ready to fully embrace the implications of such a violent, hot origin. It was a missed connection, a lost opportunity, a genuine scientific tragedy. Then, more than a decade later, the narrative shifts, building a quiet tension. In the early 1960s, at Princeton University, physicist Robert Dicke and his brilliant team, which included the young P.J.E. Peebles, independently re-derived the exact same theory. Unaware of the earlier forgotten work by Gamow, Alpher, and Herman, Dicke's group came to the identical conclusion: the universe should be awash in this cosmic afterglow. Driven by this conviction, they began a painstaking project, constructing a specialized antenna, a device known as a Dicke radiometer, explicitly designed to hunt for this primordial echo. They were on the very precipice of discovery, building the instrument that would capture the faint whispers of creation, when destiny, in its infinite irony, intervened. At the very same time, just an hour's drive north in New Jersey, two other scientists, Arno Penzias and Robert Wilson, were working for Bell Labs in 1964. Their mission was entirely different. They were testing a cutting-edge horn antenna, built for groundbreaking satellite communication experiments. But their work was plagued by a persistent, annoying problem: a low, steady hiss emanating from their state-of-the-art instrument. It wasn't the kind of static you could simply filter out. It was everywhere, coming from every direction, at every hour of the day or night. They were meticulous in their efforts to eliminate this unwanted interference. They scoured their equipment, checked every circuit, every cable. They even pointed the antenna towards New York City, attempting to pinpoint terrestrial radio interference. Still, the hiss persisted, a baffling, omnipresent whisper. In perhaps the most famous anecdote in modern astronomy, they suspected the source might be more biological than electronic. Finding two pigeons nesting inside the large horn, they meticulously cleaned out the antenna, removing what they rather delicately referred to as white dielectric material, the pigeons' droppings, convinced this was the cause. But even after their avian occupants were evicted and the antenna sparkled, the maddening, inexplicable hiss remained. It was a chance phone call, a moment of cosmic serendipity that brought these two disparate narratives crashing together. Penzias, bewildered by the persistent noise, called a colleague who suggested he speak to Robert Dicke's team at Princeton. When Penzias described the uniform, low-level microwave hiss they were detecting, Dicke's team immediately understood. The stunning, almost heartbreaking realization dawned on them. Penzias and Wilson had accidentally found exactly what they had been building a dedicated instrument to search for. They had been scooped, not by a competitor, but by a pair of engineers troubleshooting a technical problem. But this hiss was far more than just annoying background noise, and infinitely more significant than pigeon droppings. It was the cosmic microwave background, the single most powerful piece of evidence for the Big Bang theory. It is, in essence, a direct photograph of the universe when it was just a cosmic infant, a mere 380,000 years old. Before this pivotal moment, the universe was an unimaginably hot, dense plasma, a superheated fog of charged particles where light could not travel freely. It was opaque, like peering into the heart of a star. But as the universe expanded and cooled, reaching a temperature of roughly 3,000 Kelvin, electrons and protons finally combined to form stable, neutral hydrogen atoms. This event, known as recombination, suddenly allowed photons, light particles, to escape, to stream freely across the cosmos. This is the light we detect today as the cosmic microwave background. What makes this ancient light so profound, so utterly indispensable to our understanding of the cosmos, are its tiny temperature fluctuations. These are not random static. They are the literal fingerprints of the early universe, incredibly subtle variations in density that were present at the moment of recombination. These microscopic ripples, amplified by billions of years of cosmic expansion, would eventually grow into the vast, intricate web of galaxies, galaxy clusters, and superclusters we observe today. Later, dedicated space probes like COBE, WMAP, and most recently, Planck, mapped these fluctuations with astonishing precision, revealing the universe's perfect blueprint. This ancient light is a direct window into the primeval cosmos, showing us not a chaotic explosion, but a universe already pregnant with the seeds of all the structure and complexity that would one day emerge. We have tracked the universe back to an infinitesimally small, unimaginably hot point, a cosmic egg ready to hatch. But this brings us face to face with the ultimate paradox, the most profound question in our cosmic narrative. How could something so complex, so vast, so undeniably real emerge from nothing? For millennia, philosophers and thinkers have grappled with this concept, defining nothing as the absolute absence of everything, a void, an emptiness, the ultimate blank slate. It was believed to be the ultimate quiet, the perfect stillness. But modern physics, with its deepest insights into the fabric of reality, presents a far more radical, far more unsettling truth. Nothing is not at all what you think it is. Classical physics, the world of Newton and macroscopic objects, indeed defined a vacuum as precisely that, a void, a space utterly devoid of matter, energy, light, or even air. It was the perfect emptiness, a state of absolute zero activity. But as we plunged into the quantum realm, the bizarre, counterintuitive world governing particles at the smallest scales, this comforting notion of an inert emptiness was utterly shattered. Quantum mechanics, the very bedrock of our understanding of the subatomic world, explicitly forbids such a state. It declares that truly empty space is an impossibility, a theoretical construct that simply does not exist. At the heart of this profound realization lies one of the pillars of quantum theory, Werner Heisenberg's uncertainty principle, articulated in Germany in 1927. This revolutionary principle tells us that we cannot simultaneously know with perfect precision certain pairs of properties for a particle. For instance, you cannot simultaneously know both the exact position and the exact momentum of an electron. But its application extends far beyond mere particles. It applies equally to energy and time. This means that for extremely brief moments, energy can actually be borrowed from the universe, allowing particles to spontaneously appear, as long as that borrowed energy is paid back almost instantly. The shorter the time interval, the more energy can be borrowed. This extraordinary consequence fundamentally redefines what we perceive as empty space. Instead of a silent void, quantum mechanics reveals a seething, churning cosmic broth, a quantum foam, where the fabric of reality is perpetually agitated. It is a place of ceaseless, chaotic activity, where pairs of virtual particles and their antiparticles constantly, spontaneously pop into existence, borrowed from the energy of the vacuum itself. They exist for an unimaginably fleeting moment, a mere blink of an eye on a scale we can barely comprehend, before annihilating each other and returning the borrowed energy. It is as if space itself is constantly bubbling, a vibrant, energetic tableau of creation and annihilation, all in strict compliance with the inviolable laws of physics. To make this abstract, almost unbelievable idea tangible, to pull it from the realm of theoretical conjecture into the undeniable light of empirical proof, we turn to a remarkable phenomenon, the Casimir effect. Predicted by the brilliant Dutch physicist Hendrik Casimir in 1948, this effect offered a measurable, real-world demonstration that the quantum vacuum is anything but empty. The experimental setup is deceptively simple, yet its implications are monumental. Envision two incredibly smooth, uncharged parallel metal plates, brought almost infinitesimally close to each other in a perfect vacuum, a separation often measured in mere nanometers, perhaps a few hundred thousandths of a human hair's width. According to classical physics, with no charges and no external forces, these plates should simply hang motionless. But when scientists perform this experiment, the plates are unmistakably pushed together, drawn towards each other by an invisible, inexplicable force. What is happening? The explanation lies in the teeming activity of the quantum foam. Outside the plates, virtual particles of all wavelengths can spontaneously appear and disappear. But in the tiny gap between the plates, only virtual particles with wavelengths that precisely fit into that minuscule space can exist. It is akin to a cosmic filter. This restriction means there are fewer virtual particles popping in and out of existence between the plates compared to the vast unrestricted space outside them. The resulting imbalance creates a net pressure, a subtle but persistent push from the virtual particles on the outside, forcing the plates inward. This astonishing experimental evidence is not some theoretical anomaly. It is a direct, undeniable confirmation that the quantum vacuum is a physical entity, a dynamic plenum of activity, rather than a passive void. It proves that what we once conceived of as nothing is, in fact, the ground state of reality itself, a state of minimum energy, yet one brimming with an intrinsic, latent potential. It is not an absence, but a restless, energetic backdrop, a cosmic stage upon which a universe could, and eventually would, be born. If the quantum vacuum, a frothing sea of virtual particles, offers the fertile ground for creation, then what, exactly, provided the spark? What powerful mechanism ignited the universe from a state of raw, simmering potential into the cosmos we inhabit today? The answer lies in one of the most elegant and profound concepts in all of physics, the shattering of perfect symmetry. This grand rupture, a cosmic phase transition, was the true engine of the Big Bang. To grasp this fundamental idea, consider the seemingly simple act of a spinning top. When perfectly balanced and rotating at high speed, it exhibits an exquisite symmetry. From any angle, it appears the same. Its state is uniform, isotropic, indistinguishable. This highly symmetrical state, however, is inherently unstable, a precarious balance of high energy. The top, in this perfect spin, holds a vast amount of potential, but as it inevitably slows, losing energy to friction, it reaches a critical point. Its perfect balance breaks, it begins to wobble, and then, with a definitive tilt, it topples. It falls in one specific, random direction, a choice born from the slightest perturbation. This act of toppling represents the breaking of its initial symmetry, releasing its stored energy and settling into a lower, far more stable energy state. The universe, in its earliest moments, underwent a transition far more cataclysmic than a falling top, yet remarkably similar in principle. Let us scale this principle up to the unimaginable canvas of the primordial cosmos. Particle physicists, through what are known as grand unified theories, or GUT, postulate a universe in its very first, fleeting fraction of a second, an instant so brief it defies human comprehension. At this epoch, temperatures were so astronomically high, reaching perhaps 10 to the power of 27 Kelvin, that is, a 1 followed by 27 zeros, that the four fundamental forces of nature we recognize today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not distinct entities. Instead, they were merged, woven together into a single, unified superforce, existing in a state of perfect, almost pristine, symmetry. The universe at this point was like our perfectly balanced spinning top, a false vacuum state, symmetrical but teeming with unstable, high energy. This cosmic scenario finds a striking parallel in a more familiar phenomenon, a phase transition. Consider supercooled water, chilled below its freezing point, yet remaining stubbornly liquid. It is in an unstable state, holding excess energy. The slightest disturbance, a tiny dust particle, a subtle vibration, can instantly trigger a dramatic change. In a blink, the water undergoes a catastrophic shift, solidifying into ice, releasing its latent heat, and settling into a lower energy, more ordered state. This sudden transformation, from one phase to another, is precisely what occurred in the universe's infancy. As the primordial universe, driven by its initial extreme energy, expanded and cooled, it reached critical thresholds. In an event that was anything but gentle, it underwent a series of cataclysmic phase transitions. This was the grand rupture. The initial, perfect symmetry of the superforce was shattered. Like the spinning top falling, or supercooled water suddenly freezing, the universe chose a new, lower energy state. This epochal event caused the fundamental forces to freeze out and separate from each other, each revealing its distinct properties. From a single, undifferentiated force, the distinct laws governing electromagnetism, nuclear interactions, and eventually gravity began to emerge. This profound symmetry-breaking event is the cornerstone of the theory of cosmic inflation, proposed independently by Alan Guth of the United States in 1980, and Andrei Linde, originally from Russia, later working in the United States, in 1981. Their theory posits that this cosmic phase transition released an almost inconceivable amount of energy. This energy, rather than scattering matter, drove an extraordinary period of exponential, faster-than-light expansion of space itself. In a mere fraction of a second, perhaps lasting only 10 to the power of -32 seconds, a decimal point followed by 31 zeros before the first digit, the universe expanded by a factor of at least 10 to the power of 26, growing from smaller than an atom to roughly the size of a grapefruit. This inflationary burst was far more than just a rapid expansion. It fundamentally shaped the cosmos we inhabit. Not only did it create all the matter and energy we observe today, essentially stretching the quantum vacuum and its virtual particles into real ones, but it also performed an astonishing feat. It took the microscopic quantum fluctuations inherent in the vacuum, the tiny subatomic ripples in reality, and stretched them, magnifying them into macroscopic seeds of cosmic structure. These infinitesimally small variations in energy density became the blueprints for everything that followed. The vast clusters of galaxies, the individual galaxies themselves, the stars, and eventually, the planets. Furthermore, this inflationary epoch smoothed out any initial irregularities, explaining the remarkable large-scale uniformity of the universe, providing a missing mechanical link between the quantum nothing we explored in the previous chapter and the everything that cascaded into existence. Every second that ticks by, every fleeting moment, moves us irrevocably forward. We wake knowing yesterday happened, able to recall its triumphs and its trials. Yet, the future remains a blank canvas, a realm of infinite possibilities we can only anticipate, never truly remember. Why is this so? Why does time, the most fundamental dimension of our existence, possess an undeniable, relentless arrow, always pointing from past to future? This is not merely a philosophical musing, but one of the deepest, most perplexing mysteries at the very heart of physics, a cosmic riddle whose answer is intrinsically woven into the very fabric of the Big Bang itself. To uncover this profound secret, we must turn to a foundational principle of the universe, the second law of thermodynamics. This law, in its elegant simplicity, governs the direction of all spontaneous processes. It was Ludwig Boltzmann, the brilliant Austrian physicist of the late 19th century, who articulated it in its statistical form. The total entropy of a closed system will always, inevitably, increase. Entropy, in its most accessible definition, is a measure of disorder, of the dispersal of energy, of the number of ways a system can be arranged. Consider an everyday example. An egg, once whole and pristine, can be easily scrambled into an indistinguishable, chaotic mess. But has anyone ever witnessed a scrambled egg spontaneously unscrambling itself, returning to its perfect, unbroken form? The answer is a resounding no. Or think of a grand, intricate building, standing proudly for centuries. Time, weather, and neglect will inevitably cause it to crumble, its finely ordered structure collapsing into a pile of dust and debris. Yet, that dust will never, on its own, reassemble itself into the towering edifice it once was. These mundane observations are profound manifestations of entropy's relentless march. Disorder, on a fundamental level, always increases. This unwavering cosmic rule presents us with an astonishing, almost paradoxical puzzle. If the universe, as a vast, closed system, is continually progressing towards a state of maximum disorder, often referred to as heat death, then logically, it must have begun in a state of extraordinarily low entropy. This implies an initial condition of near-perfect order, an incredibly organized state from which all subsequent complexity and disorder could emerge. This seems strikingly counterintuitive, does it not? The Big Bang, that momentous genesis, is so often visualized as a cataclysmic, chaotic explosion, a violent burst of energy that would seem to imply the ultimate state of disorder. Here, the modern perspective championed by physicists such as the contemporary British luminary Roger Penrose offers a crucial insight. The initial order of the universe, he argues, was not in the precise arrangement of its particles in space. That would indeed imply a highly improbable, almost miraculous particle configuration. Instead, the astonishing order of the early cosmos lay in its gravitational state. The primordial universe, moments after the inflationary burst, was not a turbulent, lumpy chaos. On the contrary, it was incredibly smooth and uniform, a remarkably even distribution of matter and energy across vast scales. This state of profound smoothness represents an extraordinarily low gravitational entropy. All the complex structure we observe around us today, the glittering stars, the majestic spiral galaxies, the enigmatic black holes, and the vast cosmic web that connects them, are the direct result of gravity pulling matter together. As gravity inexorably draws dispersed matter into dense clumps, creating local pockets of order like galaxies or solar systems, it simultaneously vastly increases the overall entropy of the universe. This process releases gravitational potential energy, which dissipates into heat and radiation, contributing to the ever-increasing disorder of the cosmos as a whole. A galaxy, while internally structured, is an engine of entropy generation for the universe. Therefore, it is the Big Bang's unique, almost impossibly low entropy initial condition that effectively wound up the cosmic clock. It set the universe in motion with an immense potential for increasing disorder, much like a tightly coiled spring holds immense potential energy. This initial state is the fundamental reason we experience the irreversible flow of time itself. Without this low entropy beginning, without this cosmic potential to unwind, the arrow of time would simply cease to exist, or perhaps point in no discernible direction at all. Our very existence, our ability to remember the past and anticipate the future, is not some accidental byproduct, but a direct consequence of this ongoing, universe-wide process of increasing disorder that was set in motion 13.8 billion years ago. The cosmic symphony, as we have come to understand it, plays out across immense scales of space and time, a dramatic narrative from a singularity to the vast, expanding cosmos we inhabit. But as we delve deeper into the universe's operating manual, a profound and unsettling question emerges, one that challenges our very notions of chance and design. Why does this symphony sound so perfect? Why are the fundamental constants of nature, the speed of light, the strength of gravity, the precise mass of an electron, the delicate balance of the cosmological constant, tuned with such breathtaking precision as if to allow for the very existence of stars, planets, and even life? This is not a mere scientific curiosity, it is a profound puzzle known as the fine-tuning problem. It is as if the universe's control panel has 1,000 dials, and each one must be set to an incredibly specific, narrow range for anything complex to form. A minuscule alteration to the strength of gravity, for instance, a change as small as 1 part in 10 to the power of 40, would either cause the universe to collapse immediately or expand so rapidly that matter could never clump together into galaxies. Adjust the charge of an electron by even a tiny fraction, and the chemistry necessary for life would become impossible. The cosmological constant, the enigmatic force driving the universe's accelerating expansion, is so extraordinarily small that if it were just slightly larger, the cosmos would have ripped itself apart before any structures could form. It is a cosmic coincidence of such staggering improbability that it demands an explanation, yet one that remains within the realm of scientific inquiry, far from any supernatural invocation. One of the most audacious and compelling hypotheses aiming to solve this enigma plunges us into the realm of the multiverse. This concept stems, in part, from string theory, a leading contender for a theory of everything that postulates that the fundamental particles of our universe are not point-like, but rather tiny, vibrating strings. String theory suggests a mind-bending possibility. There might not be just one set of physical laws, but a colossal landscape of potential universes. Picture a vast, almost infinite mountain range, not of rock and soil, but of mathematical possibilities. Each peak, each valley, each subtle fold in this landscape represents a different stable vacuum state, a unique configuration of fundamental laws and constants. The sheer number of these possibilities is staggering, perhaps 10 to the power of 500, that is, a 1 followed by 500 zeros, a number so immense it dwarfs the total number of atoms in our observable universe. And how might these countless universes come into being? Through a mechanism known as eternal inflation, a concept brilliantly elaborated by physicist André Linde. If the inflationary period that birthed our universe never truly ended everywhere, If pockets of space continue to inflate and generate new regions of reality, then new bubble universes could be constantly spawning from the quantum vacuum, much like steam endlessly rising from boiling water. Each of these nascent universes would then realize one of the myriad possibilities on the string theory landscape, settling into its own unique set of physical laws and constants. In this grand, sprawling cosmic tapestry, the fine-tuning problem transforms. We find ourselves in a universe perfectly suited for life, not because it was specially designed, but for the simple, almost tautological reason that we could not exist to observe it otherwise. This concept is known as the anthropic principle. It is the equivalent of a fish asking why its pond is so perfectly watery. The pond is not watery for the fish. The fish exists because it evolved in water. Similarly, we find ourselves in a universe with life-permitting laws because we are the products of those very laws. In a multiverse of 10 to the power of 500 possibilities, it is not surprising that at least one, or many, would possess the precise conditions for stars, planets, and conscious beings to emerge. But the frontiers of physics offer other equally mind-bending ideas, challenging our very perception of reality. As a contrasting, yet equally profound hypothesis, consider the holographic principle. Pioneered by Dutch physicist Gerard Hooft in 1993 and further developed by American physicist Leonard Susskind in 1995, this concept suggests that our entire three-dimensional universe, with all its stars, galaxies, and even ourselves, might actually be a projection. It posits that all the information describing our three-dimensional reality could be encoded on a distant, two-dimensional boundary, much like a three-dimensional hologram is created from information stored on a flat, two-dimensional surface. Think of it this way: the seemingly solid, tangible world we experience might be nothing more than an elaborate illusion, a cosmic cinema showing a projection from a flat screen billions of light-years away. This isn't science fiction. It is a serious, mathematically consistent idea emerging from the study of black holes and quantum gravity. The information content of a black hole, for instance, appears to be proportional to its surface area, not its volume, hinting that gravity itself might be an emergent property of information encoded on a boundary. While deeply theoretical and still very much under investigation, the holographic principle offers a radical reinterpretation of what reality truly is, suggesting a universe far stranger and more complex than we can yet fully grasp. These ideas, the multiverse, the anthropic principle, the holographic principle, are not yet proven facts, but they represent the leading battlegrounds of theoretical physics, where the most brilliant minds strive to unravel our ultimate place in a cosmos that continues to defy our expectations. Every story has a beginning. But what if the greatest story ever told, the epic of our universe, isn't about a single, thunderous start, but a continuous unfolding, a saga that, even after billions of years, is still writing itself? We have journeyed through the intellectual battlegrounds where the very idea of a cosmic origin was once resisted, dismissed as abominable physics. We followed the faint, red-shifted light of receding galaxies, the undeniable forensic evidence that our universe is not static, but expanding, always expanding. And we listened to the ghostly echo of creation itself, the cosmic microwave background, a photograph of the universe in its infancy, barely 380,000 years old. Now we weave these threads together, attempting to synthesize the most profound narrative known to science. The core revelation, the ultimate reframing of our cosmic birth, is this: the universe did not burst forth from an absolute void, from a classical definition of nothingness. Instead, it unfolded from a state of ultimate simplicity, a primordial canvas pregnant with all potential. Consider this initial state not as an empty slate, but as a perfectly symmetric, information-poor, low-entropy, false vacuum. This might sound abstract, but it is the cosmic equivalent of a tightly coiled spring, holding immense potential energy, yet appearing deceptively simple on the surface. It was a universe brimming with latent possibilities, a cosmic seed containing the blueprint for everything that would ever be. The Big Bang, therefore, was not a creation ex nihilo, not a sudden appearance from absolute nothingness, but rather a profound phase transition. It was a rupture in that initial, perfect symmetry, an event that unleashed the staggering complexity hidden within that profound simplicity. We can now connect the dots, tracing the lineage of our existence back to these earliest moments. It was the shattering of this initial symmetry that gave birth to the fundamental forces of nature we recognize today: gravity, electromagnetism, and the strong and weak nuclear forces, each peeling away from a unified superforce like distinct colors emerging from pure white light. Then, the period of cosmic inflation, that unimaginably rapid expansion, translated the microscopic quantum potential of the vacuum into the macroscopic seeds of cosmic structure, literally stretching subatomic ripples into the grand scaffolding upon which galaxies would eventually coalesce. And crucially, it was that astonishingly low entropy beginning, that initial state of near-perfect order, that wound up the cosmic clock, creating the irreversible flow of time itself, providing the fundamental reason we experience a past, a present, and a future. The universe's story is, at its deepest level, a story of information. From a state of almost zero information, a universe so uniform and simple that there was little to distinguish one point from another, it has been blossoming for 13.8 billion years. Its information content has been growing, organizing itself into ever more intricate patterns, first elementary particles, then atoms, then vast galaxies housing hundreds of billions of stars, planets orbiting those stars, and eventually, on at least one of those planets, conscious beings capable of piecing together this very narrative. Think of it like this: if the initial universe was a single, perfect binary digit, a lone 0 or 1, then today, it is the most complex, interconnected supercomputer imaginable, still computing, still evolving, still revealing new layers of its programming. We, the observers, are not just passive witnesses to this cosmic drama. We are its most intricate products, born of the very laws and processes we now strive to comprehend. Our existence is a testament to the universe's incredible capacity for self-organization, for the spontaneous emergence of order from chaos, complexity from simplicity. And yet, even with this profound understanding, the story is far from over. The cosmos continues to hold its secrets close. The enigmatic whispers of dark matter, the mysterious acceleration driven by dark energy, and the mind-bending possibility of a multiverse, a vast ocean of bubble universes beyond our own, all serve as powerful reminders of the immense intellectual humility required to truly engage with the universe. Our emergence from the simplest possible something was merely the beginning of an epic, an ongoing saga of unfolding complexity. And we are the fortunate few, privileged to look back, to marvel, and to continue the timeless quest to understand our place in this unfolding cosmic tapestry.